Welcome to This Climate Business, the podcast about turning the climate crisis into an opportunity. I'm Vincent Heringer. Every week, I talk to entrepreneurs, investors and experts about what they're doing to solve the climate crisis and get New Zealand down to zero emissions by 2050 or sooner. This Climate Business is brought to you by Podcasts New Zealand. This week I'm joined by Professor Dave Frame, Director of the New Zealand Climate Change Research Institute at Victoria University, and he was a lead author on the 6th assessment report of the Intergovernmental Panel on Climate Change, the IPCC. And of course, this is the third part in our series on the IPCC report. And I thought that Professor Dave could give us an insider's view, given that he's written part of it, an insider's view on how the IPCC works and also on actually the science of warming and especially the role of methane, given it's such a hot topic in New Zealand. And I would be hard-pressed to find someone more qualified. Dave has a background in physics and philosophy and policy. His previous posts have included research positions at the University of Oxford's Department of Physics and Geography and as Deputy Director at the Smith School of Enterprise and Environment. He's also worked at the New Zealand Treasury and served as a secondment at the UK Department of Energy and Climate Change. And as I mentioned, he'd been a lead author on both the 5th and 6th assessment reports of the IPCC. So it's quite a mouthful, isn't it, Dave? But welcome to This Climate Business.
Oh, yes. Thanks for having me along.
So very lucky, actually, for you. You can order some takeaways, and I can't because I'm talking to you at lockdown 4 and you're in lockdown 2.
Yeah, it's certainly a strange world at the moment, isn't it? It's takes some managing on the fly, I guess.
Yeah, I think it does. Well, we're very good at it now. I'm really curious about the way these reports get put together. They seem like an incredible logistics exercise. Could you tell us a bit about what being a lead author actually means?
We write the text that goes into the chapters. So there's a group of normally about 15. In the physical science report, there's about 15 people on a chapter. There are a couple of coordinating lead authors whose job it is to pull it all together and to take the structure that's been agreed on by the technical support unit and the co-chairs of the working group. And you know, they kind of agree an outline, and then they pass it to the coordinating lead authors, and then the coordinating lead authors use the resources at their disposal to write, to flesh that out and turn that into an actual report. So in the previous one, I was on chapter 1, which was the introduction, which was a lot of fun because it was a very general remit. And this time I was on chapter 7, which was a great chapter to be on. I think it's really central to a whole bunch of live science policy issues. It was a chapter primarily about climate sensitivity. So that's if you double the amount of CO2 in the atmosphere from pre-industrial levels, how much does the world warm? So that was our overall topic, and we had some subtopics within that.
What's the experience of being working together with your colleagues or your peers on this? Is it a collegial exercise? Is it a combative exercise?
Oh, it can be either or both. It's natural that scientists naturally find sites of disagreement, but within the chapters, I've been very lucky that the chapters I've been on have been really harmonious and a great group to work with. And I think this time especially, we had a lot of fun writing it together. There was a real sense of camaraderie among the people writing it. Experiences with other working groups and other parts of the report can be a bit more variable. It varies chapter by chapter. I didn't have a great time working with Working Group 3 on this, but you kind of expect that. It won't always be plain sailing, and the closer you are to policy issues, the less plain sailing you can expect.
Right. So because the science is reasonably, uncontroversial now, would that be too far a bow to stretch?
It depends which bit of the science you're talking about, but the basic proposition that that greenhouse gases are driving the warming is absolutely uncontroversial. I think that's pretty clear. I think the fifth assessment put it really well when they said human influence on the climate system is clear. That stuff is all really obvious. There are when you come to talk about some of the details and some of the especially issues to do with priorities, then it depends on how you look at it.
Yes. The report makes goes to great pains to point out how accurate the models have become and the simulations as well. Could you explain why have those models improved, and is there a difference between the models and the simulations?
Well, the models run simulations. The models are fed some input parameters. They evolve in time. The state of the climate in the models evolves in time, and they have got better and better. They've had the best of the models have had 30 years of development and a lot of money spent on them. And they started out as weather models that had a lot stripped out, and that had they had the basic principles of physics in them. But as we've got more and more computing power, we've been able to do that stuff at finer scales and introduce more and more of the scientific components that we know matter in the climate system. Clouds are still a thing. Clouds are always a thing because real clouds operate on scales smaller than we can model, and that's been the outstanding uncertainty in the kind of overall response. But we're getting better.
Yeah. Can I ask a really dumb question? And I'm sorry if my listeners think that this is such a kindergarten question. Feel free to skip ahead. But we know that the climate record, in terms of our modern scientific recordings of weather, is what, maybe 200 years old. How can we know with such certainty back thousands, tens of thousands, millions of years old? What are the data points that we rely on to gather that knowledge?
Well, our knowledge becomes more uncertain the further back you go. So we've got great global coverage in the satellite era. So the part we're most confident about is naturally the recent past, when we've spent the most, when we've had the best observational network. As you go further back, you're left with surface temperature records, and those are spatially not necessarily very representative. So you can sample ocean temperatures. The sea covers 70% of the Earth's surface, and you're left with ship tracks which don't go into the polar regions and so on. So there are, the further back you go, the sparser the data. And then once you're in the pre-instrumental period, you have things like tree rings and ice cores and other things which require further stages of inference about how you take those and turn them into things like temperatures and stuff like that. So, the further back you go, the greater the data challenge. But some of the really dim and distant past paleo climate signals are very large, and so even though the noise is very large, so is the signal. And so that stuff can play a useful role augmenting what we understand about the climate system. But that last 150 years, you can't explain the warming that we've seen without finding a role for greenhouse gases. So that stuff on its own pretty much tells you that climate change is real and driven by greenhouse gases.
We're told, for instance, that and you see it in those incredible graphs, that we are living in a period where carbon dioxide is now at a concentration that it hasn't been for what, 2 million years, I think was the number I read. How does that number come about? How do we know what the concentration of CO2 was 2 million years ago?
Well, they use a range of things that have like ice cores and what have you, where they can get at the air that has been trapped within those, like little bubbles of air trapped in ice, and then they figure out what the temperature of that air was, plus or minus, and they also have CO2 partial pressures, so they can get the CO2 concentrations and the air temperature. Of course, that's only a local thing, and then you need to go beyond that and have a whole bunch of those data from different parts of the world to get at what you think the global temperature might have been in those days.
And I suppose you're getting these measurements from all over the world, not just one location. And is it a bit like geology where, kind of each point kind of builds on itself until you start to get a coherent picture?
Yeah, they have all sorts of paleoclimate archives. There's been a lot done in that area in the last 30 years, and globally what they kind of try and assemble some sort of picture of different periods and figure out what different regions were, what their climates were like in those periods. Models try and synthesize that and put them into a more physically coherent story. But really, most of the evidence comes from the recent past, where we have the instrumental records, and we're a bit more confident about what the surface climate was like across the world.
So, what is the causal relationship between our human emitted CO2 and warming? I think we probably know why it happens, but what's the evidence for one coming before the other and it not just being kind of coincidence? Well,
in the case of the last 150 years or so, if you run climate models with only natural forcing, so that's with the solar cycle and volcanoes, you don't get a warming across that period under any conditions. It's only if you include greenhouse gases as observed, or anthropogenic influences as a whole, so that's aerosols which cool the climate and greenhouse gases which warm the climate. And what you find then when you add all the forcings, so the natural forcings plus the anthropogenic ones, is that the world warms. And it's not a surprise the world warms. Some pretty simple physics is governing that trapping of heat, and it has to do with how opaque the atmosphere is at long waves, the long waves at which the Earth is re-radiating out to space, compared with the short wave, that is the ability of the transmittance of the atmosphere at the radiation at the wavelengths where the sun is actually shining. So the kind of that's the standard way of doing it is to consider an atmosphere where the sun is shining on the Earth receives radiation, the Earth tries to get rid of that radiation by radiating it to space, and the greenhouse gases in effect hamper that process, and therefore the atmosphere and the surface retain more energy.
And the only explanation for that incredible growth and concentration of carbon dioxide, especially, is this human contribution through the release of fossil fuels.
Yeah, absolutely. Yeah, it's clearly what's driving it, and so that comparison between a world with greenhouse gas influence and a world without, they form the basis of what we call detection and attribution studies, where we try and detect whether or not there's a signal of change, and then attribute it to different causes by considering one cause at a time, and then several causes together, and working our way through that inferential process. And really, the world is warming. That's really clear. We have some really simple physics that translates well into models, and that explains that warming. And there are no major discrepancies between the warming we see and our basic physical story. So it's not an area where there's some massive controversy and we're not quite sure what's going on. It's a pretty simple physical process, and human behavior is driving those emissions, which are driving increases in concentrations, which are then changing the radiative balance of the atmosphere.
If it looks like a duck and it quacks like a duck, it probably is.
Yeah, it's almost certainly a duck. In this case, I mean, we've got so much information that it's a duck. There's not a lot of point in sitting around and pretending it's something else.
Yeah. Tell us about Chapter 7. What were you studying, and put you on the spot to see if you can summarize what you concluded.
Well, actually, we were summarizing what I was just talking about. We were summarizing the Earth's energy balance, its imbalance, the response to a doubling of CO2 and a few other what we call different sorts of ways of summarizing that global response. And we were also writing around a few other things like ocean heat uptake, because a lot of that energy imbalance a lot of the energy that has been trapped has gone into the ocean, about 91% or something. And we also looked briefly at the role of, because we had a general remit in terms of metrics of greenhouse of warming, we also looked at emissions metrics, which is where the stuff to do with short-lived gases versus long-lived gases comes in, which is in New Zealand that plays out as the methane issue.
Yes, we're going to come to methane in a minute. What are the if I ran through them, we are seeing the kind of the main outcomes of this increase in concentration of CO2 especially, but not only that, other greenhouse gases. The surface temperature increases, and I guess this is where we're talking about the 1.5, the 2 degrees kind of average increases.
Yep.
Also, water temperature is rising, sea temperature. Is that correct?
Yes, that's right. Yep, surface temperatures are rising. Yep.
Yes, which then also leads to expansion, I suppose. Warm water expands, and that, in addition to the melting of ice areas, is contributing to our rising sea levels.
Yeah, and at the moment, I think thermal expansion is the largest term. So if you heat water, it expands. That's why your hot water cylinder has a little overflow valve. So there's, when I say that a lot of this stuff's simple physics, it's pretty simple, all right.
Even I understand it. Acidification of the ocean, how does that work? Is that to do with the absorption of more carbon dioxide? So you're getting what, carbolic acid?
Yeah, exactly. It's a chemical thing rather than a physical thing. So the ocean acidification is a problem that is also driven by the accumulation of CO2 in the atmosphere, and then because it's in the atmosphere, hence in the surface layers of the ocean, because they exchange signals, and that acidification then plays a role in decreasing the efficiency of a bunch of processes, marine biology processes in those layers. And so it's a problem that runs in parallel and has the same cause as warming, but it's not exactly the same thing. And it's a chemistry problem rather than a physics problem, which is, the warming is a physics problem. But it has the greenhouse gas, primarily, or the CO2 increase, is the thing driving that.
If only the planet could tell a difference between a chemistry problem and a physics problem, it would be fine. The other major effect, and I wonder if this was in your in Chapter 7 as well, was the impact on glaciers, which seems to be only in one direction.
Well, yeah, that's one for Nick Gollage, actually, my colleague here at Vic. He's so that stuff's been plays out mainly locally as a glacier problem, and then as sea level rise as well. Glaciers contribute to sea level rise. That wasn't one we dealt with. We were kind of the four main things that determine the overall scale of the response are a bunch of feedbacks. The water vapor and lapse rate feedback, which act together. So if you heat the surface layers of the ocean, you get more evaporation, you get more water vapor. That goes up to the upper atmosphere, and then it releases energy when it turns from water vapor back into droplets. Those two effects act jointly. They're very important in the tropics, and they govern part of the amplitude of the response. The surface albedo, so as you change the vegetation or as you change vegetation, you change the shininess or the absorptive, how much the surface absorbs and how much it reflects. And that contributes to further warming. And then clouds, which are also can potentially warm and can warm, and they do warm the climate, and they also cool the climate. And the exact ratio the exact mix is the thing that climate models kind of argue about the most, and in which, if you actually think through the contributions to the overall response, it tends to be cloud radiative feedbacks that you spend most of your time on. But those things, water vapor and lapse rate, albedo feedbacks, a good example of an albedo feedback is sea ice. If you melt all the sea ice in the Arctic, you have a blue surface instead of a shiny surface, and so that enhances warming, and clouds as well. So those are the sorts of things we were discussing, a lot in the chapter, because those are the primary feedbacks within the climate system. Chapter 5 also considered feedbacks within the carbon cycle feedbacks, which play an important role in determining carbon budgets. If you take the stuff in Chapter 7 and the stuff in Chapter 5, that's basically how you do carbon budgets.
Right. Yeah. Okay. We're going to come to methane, I promise, in a minute. But just on that albedo effect, there's quite a few examples of people. I just read, for instance, the other day in the Swiss Alps, they were covering a glacier with a thermal blanket that acted both as a insulator, but also worked to reflect the sun. You hear also of, I think I saw in Sydney, a law change that roofs are now required to be painted in a lighter colour. Yeah. Are these kind of measures, they sound worthy, up against the climate system? Are those kind of gestures, are they more than gestures? Could they actually make a difference?
I think the ultimate solution to warming, the ultimate way we have to stop the warming, is to stop emitting fossil fuels, fossil carbon, basically. And that is, I don't think anybody really seriously disagrees with that. Other initiatives can contribute. If you paint something shiny rather than dark, then you do backscatter radiation, and that's then you're reducing the forcing per unit area, the radiative forcing. But it's a little bit like a home geoengineering project in a way. Yeah. And maybe you're actually dealing with that shortwave I talked about before. You're giving a shortwave answer to a long wave question. The real problem in the system is this radiation from the Earth. Once it's been heated by the sun, the radiation can't get out as easily as it could. And simply backscattering more radiation on the way in is that kind of, like I say, shortwave answer to a long wave question. So, there are a bunch of things you can do. I once worked out about 15 years ago how much tinfoil I would need to, if I bought a bit of Australia and put tinfoil down and changed from red to silver, how much would I need to offset my overall lifetime forcing? And it was kind of an interesting, fun thing to do, but I wouldn't seriously suggest, it's not a scalable answer, right? It's just like I say, it's a homegrown geoengineering project, and maybe there's a role for that stuff, but it's not the main event.
I think Rio Tinto would be totally supportive.
Yeah, it's striking how many of firms like that are enthusiastic about doing anything but the thing they need to do. So, yeah.
Yeah, that is, we talked about that last week on the show with Rod Oram, how frustrating it is that we can isolate it, which big businesses are having the most effect and how resistant to change they are. Before we get to methane, tell me about water vapor. So explain the theory of how water vapor increases as a result of warming. I mean, it kind of stands to reason, I suppose, if you've done your fourth form physics. But then how does that contribute to a feedback effect?
Well, if you heat the Earth and you get more water vapor in the air because the surface is warmer, so you get a greater vapor flux coming out. That then, because water vapor itself is quite a strong greenhouse gas, that is a case of carbon stimulating a warming, which is then re-stimulated by a second effect, which is the water vapor effect. So it's the fact that water vapor itself is a strong greenhouse gas, and you've put more water vapor in the atmosphere, so you've put up, in effect, another greenhouse gas. It acts together. Tropical convection, half the Earth's surface is tropics, right? From about 30 north to 30 south is 50% of the Earth's land area or surface area. And the convection that goes on in the tropics is a really important part of the story. And that tropical convection, then what happens, you get that water vapor, you chuck it up to the top of the atmosphere through convection, those big thunder clouds you see in the tropics. And then it has a phase change where that vapor turns back into liquid, back into rain, and that itself is releasing further energy aloft. So that's actually a negative feedback, on the warming, but it acts jointly with the water vapor feedback to give you an overall positive feedback. This is more climate physics than I was expecting, I have to say. I hope your listeners aren't turning off.
No, that's exactly why we have you on the show, so that you could explain the stuff to us. Is the water vapor and this feedback effect, is that what is contributing to the increase in the kind of sudden rainfall and these massive deluges that we are seeing around the world? Are we suddenly living in a monsoon planet?
Certainly, there's a relationship called the Clausius-Clapeyron relationship, which says
Say that again.
The Clausius-Clapeyron relationship, and it basically says that for an
it's
extra
just worth
degree,
knowing for the name, isn't it?
It's a good name. But for an extra degree of warming, the most saturated parcels of air can contain about 7% more moisture, and those saturated parcels of air are now more full of moisture than they were, and that is what is contributing to these extreme rainfall events that we're seeing. So in New Zealand, work by Luke Harrington here at the Climate Change Research Institute and Suzanne Rosier at NIWA and others has shown that that a lot of our rainfall, most of the really heavy rainfall events come as what we call atmospheric rivers out of the tropics and come blasting into New Zealand, and they're more full of water than they were, and so there's more water to dump. And when they interact with, especially with unstable meteorological conditions, just where they run into, so they make some sort of complex system by banging into something else as well as the land, you get these really, really heavy events. And we've known about these for quite a while. I would say that the research linking these extreme rainfall events and climate change goes back a good 15 years. And in New Zealand, we've been studying these for about, I think, probably about 10 years as events that are closely linked to climate change. We're beginning to build a good picture of that. And I'm actually leading a Endeavour Fund project called Whakahura, or the Emergence of Climate Change Extremes, which is looking at this as well as drought events and wildfire events and other extreme weather events.
Why is methane such a powerful greenhouse gas?
Well, there are a range of different greenhouse gases. They vary along two kind of axes. One is how effective a kilogram of that gas is at trapping radiation. And there are some of the industrial gases are really, really high, really powerful at trapping radiation. CO2 per kilogram is not especially powerful at it, which is a good thing, because otherwise, this might have got away on us before we'd got a handle on it, climate change. But methane is one of a number of gases that has quite a strong warming effect. It's not up the top end. The ones with the really, really high powerful abilities to trap radiation have global warming potentials in the thousands or tens of thousands. But methane, given its abundance, is a powerful greenhouse gas. It's also the other axis along which they vary is the residence time. And some greenhouse gases have short residence times, and some have very, very long residence times, and are in effect kind of permanent. And in the case of methane, it's a powerful greenhouse gas, much more powerful than CO2 in terms of trapping radiation, but it only lasts about 10 years or so, whereas CO2 is not characterized by a single timescale, but from a kilogram emitted from your tailpipe, about 40% or so is there after 100 years, and about 20% or so after 10,000 years, I think, something like that. So a large fraction of it is in effect permanent, and it's so that the research we've been doing, and the chapter made this fairly clear, because I don't know, this isn't scientifically controversial. There are different ways of making the comparison between these different greenhouse gases. And the basic problem is that when people try and come up with a single measure of a greenhouse gas against CO2, they're collapsing those two axes, the ability to trap radiation and the residence time, onto one. And that doesn't really do a very good job. And
so when we see in the written down a CO2e, which the E for equivalent, that is the symbol for collapsing all those. It's kind of almost like, I don't know, it wouldn't be averaging, but it's somehow grabable measure of all those different greenhouse gases.
Yep, it's based on the time integrated radiative forcing of a kilogram of some species against that of the time integrated 100-year radiative forcing of a kilogram of CO2. And so it's a ratio with no units. And it's not a very good way to make the comparison. And some people defend it as a compromise that was struck on and that people have sort of been using, and so they might as well keep going. But it was a very path-dependent thing. One of the people I was lucky enough to work with on Chapter 1 in the 5th assessment report was Don Werbels, who's from Illinois, I think. Illinois or Michigan, I think it was Illinois. Anyway, Don was on the first assessment report, and John Houghton, who was the chair of the IPCC at that point, came in one day and asked Don if he could do something like what Don had done for ozone destruction potential, the power of a chlorofluorocarbon species to destroy ozone. John asked Don if he could do something like that for the greenhouse effect, and so Don came up with this way of doing things with his students, which was called GWP. And the first assessment report made it really clear that they weren't endorsing this. They actually chose what they called a simple method to show the problems inherent in doing this, of collapsing those two axes into one. But it kind of stuck. And the question is, and in the Kyoto era, when people were looking to make small changes to emissions, or reductions of several percent rather than 100%, it probably didn't make a huge amount of difference. Scientists complained about GW. There's a long literature complaining about that CO2e or GWP 100 in the science literature, but it was pretty niche. But as you start to actually put real money on this and start to choose those priorities about what you do when to deal with climate change, the issues that arise from that collapsing of those two axes into one start to become more real. And
when you think about the New Zealand context, that we have actually a pretty good story to tell, particularly around energy, right? Which is, for most countries, the largest emitter of CO2 or of greenhouse gases is CO2 from energy. But because of our methane contribution, is that what you're saying, that there's a conflation of our data effectively, and it makes our story worse than it actually is? Is that what you're saying?
Well, I'm not sure we do. It depends whether or not we have a good story to tell depends on how you look at things. So New Zealand historically is a low CO2 country, and in theory that's a good story. The problem is most those decisions that made us a low CO2 country were made a very long time ago for reasons that had nothing to do with climate change. They were to do with developing a hydroelectric electricity supply. And so what's happened is we haven't made inroads into CO2 emissions, and we have a fairly effective price in some ways on carbon now, but for a long time, even though we had an emissions trading system, we did have a price on carbon. It's very hard to see how that's really driven things down at a rate that's consistent with the aim to stay under 2 degrees.
So it's actually hindered us in the sense that it's masked the methane contribution by conflating it with CO2 when we should have been, from a policy point of view, been more aggressive in our approach to methane much earlier.
Well, I think we should have been more aggressive to CO2 and actually drive it down. In terms of methane, because it's short-lived, it's not cumulative. So the warming is just purely cumulative in CO2. So every ton it's like lead in your blood or something like that, lead or asbestos or one of those cumulative heavy metals or other long-lived pollutants in the environment. And every kilo you emit keeps adding to the warming. Methane is more like coffee or alcohol in that it breaks down over time. And the choice of which one, in most pollution regulation, I think you would normally separate these out and have targets for short-lived and targets for long-lived. We don't make fungible permits between, you're able to, I had one less cup of coffee today, so I'll snort a little more asbestos. We don't normally trade off like that, right? That would be a weird thing to do, but it's something that, because we're in this habit, we run the risk of doing. And that would be, in my view, really dumb. And it would be really easy to leave a warmer world behind if we make trade-offs that mean we go really hard after methane and we continue our long-standing habit of not doing much on CO2 because, people drive cars, and it turns out we have a very suburban pattern of urban settlement. 85% of New Zealanders live in cities or things a bit like cities. We have a very spread out, diffuse urban form. We all drive everywhere. If you try and make meaningful inroads into that before electric cars get here, you'll pay an electoral price. But so it's much easier politically for people who don't expect a lot of votes out of the farmers anyway to go after methane. But the danger is if you leave those CO2 emissions going, and if you go after methane instead of CO2, then the danger is that you might actually leave a warmer world behind pretty easily. If you make the trade-offs at that usual CO2 equivalent number of about 28, within 40 years, you would be leaving a warmer world behind.
The farming lobby must love this message. Do you find yourself in agreement with agriculturalists?
Oh, sometimes, and sometimes not. So because it's short-lived, you can actually reduce warming quite fast by making and because it's a powerful greenhouse gas, you can actually reduce warming by reducing emissions. So you can decrease the warming that New Zealand's responsible for by making a 10, 20, 30% cut in the methane. Whereas if you make a 10, 20, 30% cut in CO2, all you do is reduce the rate at which you're warming the world. Mm-hmm. Now, taken together, the Zero Carbon Act actually, if we got to zero CO2 and nitrous oxide by 2050, net zero, and we cut methane emissions by about 35% plus or minus, which is how I interpret that 20 whatever to 47% band. It's about 35% plus or minus 12 or something. Then you would basically, New Zealand would stop its contribution to warming sometime in the late 2030s or 2040s. So that would mean that we have stopped our contribution to warming well before the Europeans, for instance, who tend to be, because they're intending to be net zero by CO2, net zero all gases, but because they are so thoroughly dominated by cumulative gases, getting to net zero for them would imply stopping the warming. They don't have the methane lever. So the point is, the current plan to reduce methane emissions by about 35% in the next 30 years, while getting all the way to 100% on all the other gases, would in effect stop our contribution to warming earlier than that of the people who regularly congratulate themselves as being world leaders.
This is not the message that we are getting typically from Europeans, but other critics of New Zealand that are pointing particularly to our agricultural emissions as unaddressed and unaccounted for.
Well, a lot depends on the He Waka Eke Noa program, and if the agricultural community can get its act together and figure out with government ways of achieving the emissions reductions that we hope to achieve, then I think that a lot of that criticism should go away, because the target itself is fine. I've never heard a European, and that includes European voices in New Zealand like Rod Oram, say, I've never heard them actually, why does New Zealand have to stop its contribution to warming before Europe? Why do we have a special obligation to given that? So the British High Commissioner said something last year about New Zealand not being up to scratch on climate policy because we weren't doing net zero the way they were. And then one of the people on the UK's Climate Change Commission, a guy called Lord Debon, John Gummer, he came out and said something similar. But actually, if we stop our contribution to warming before they do, why are we the bad guys? I've never heard a good answer to that. But in general, it's because people actually don't understand the points that they don't understand the difference between short-lived and long-lived gases well enough to know how the two interact with warming. And it's just a little frustrating that I think there's quite a lot of cultural cringe in this in New Zealand, that that people that we kind of expected to defer to overseas voices or to what the Brits say, or there are times when climate policy in New Zealand really makes me think we're 1921, not 2021, because there's just this sort of this presumption that, well, other countries have this and we're behind them, so we must do it that way. And I guess I just don't think that way.
Well, implied in what you're saying, of course, is that we do manage to curtail our transport emissions, which is no easy feat. We don't have the equivalent of a He Waka Eke Noa in transport, for instance. We don't have industry-wide collaboration with users, manufacturers, regulators, planners to aggressively set targets and figure out how we get there. What we have is a sort of hodgepodge of city governments, possibly petrol taxes, congestion charges. It sounds like what the implication, I know you're a scientist and so it's not fair to ask you what policy should be, but it sounds like in terms of priorities, you are really throwing the challenge back to our urban dwellers.
Well, yeah, I think I could see paths to reducing our methane emissions by 35%, a combination of on-farm activities, of efficiency gains, of technology. If you've got to come down by a third in 30 years, okay. But we've said we're going to come down by 100% in CO2, and forestry kind of isn't scalable for the CO2 problem. You just have to keep planting larger and larger areas if you're just going to rely on forests.
You're talking about offsetting rather than
I'm talking
reducing.
about offsetting, yeah. I mean, I think when I often go to conferences where companies talk about what they're hoping to do, and if you talk to a company and they say they're net zero, usually what's happened is they've made some efficiency gains and they are offsetting, or they're buying, in the old Kyoto days, they were buying buying permits from overseas or what have you, and saying that was net zero. And that's not really. It's not a sustainable. It may be an accounting net zero, but it's not a sustainable climate policy net zero, because if you keep emitting, you need to keep planting those trees, and you'll run out of space for the trees faster than you'll run out of fossil fuel reserves.
Well, it gets even worse than that. In California, their forests, which are acting as their carbon sinks, are now on fire.
Yeah,
and are contributing. Are now contributing to global warming because of the release of energy.
Yeah, and it's easy to do this quite badly, I think, and that's where the environmental integrity of climate policy is going to come under more and more scrutiny, because we actually need to stop the warming, and that's where the way you compare the roles of different factors in the climate system, forests, fossil emissions, other gases, becomes really, really important for that goal of actually halting the warming, which, if you go back to the Framework Convention on Climate Change, that's kind of what people have more or less agreed to do. And that's certainly what Article 2 of the Paris Agreement thinks we're doing. And how you make these comparisons becomes really important, and then it becomes partly about where you put the pressure, and that's where I think the implicit implication of a net zero target by 2050, given our transport, given our population growth, given the increased suburban sprawl we've seen, and we're probably going to see again as we try and deal with another major issue, which is the housing crisis. I just think you're putting a huge bet on technology getting you out of jail in the form of electric vehicles or hydrogen vehicles or something like that. And what's plan B? What if that stuff comes through slower than we think? How do we actually deliver on that 100% CO2 reduction? Yep, you go.
I was going to ask you, given your multidisciplinary background, you've worked in Treasury, you've spent time working in an enterprise institute. Are you finding that the interest and engagement from business, are you invited to participate? Are they seeking you out for advice and participation in how to solve this?
Sometimes, some do. It's really interesting that a lot of the kind of industry NGO things, I felt like after I started talking about methane, some of those invites dried up, and that was interesting because people clearly heard. Well, they obviously ask who they want to, but some of that, I think, was that people struggled with understanding how these different gases play a role, and among the people who really didn't like the stuff we were saying, if you look at their submissions on the Zero Carbon Act, were people like I think it was one or two of the oil companies really didn't like the option of stabilizing methane or small reductions in methane and net zero CO2, presumably because they thought that would be bad for them. So it's an interesting space. You get all sorts.
You always know that you're on the right side if the oil companies are against you. Unfortunately, that's a kind of a hint, isn't it? Mm. We need to stop talking because we're well over time. But I'm curious to know your philosophy background. What's the connection there? You don't meet many climate scientists with philosophy in their credentials.
Yeah, well, I did philosophy as a major alongside. I guess I started in. It's pretty typical story for a lot of people. I think I started doing physics, and then I did a philosophy paper taken by David Novitz at the University of Canterbury, and I really loved it, and I couldn't get enough. And so I did a full major in philosophy, but I couldn't bring myself to do philosophy of science because hearing some of the social science critiques of science, I could just about manage as an adult, but when you're actually having to plow through differential equations and tensors and things like that, the last thing you want to hear is somebody kind of with a cup of coffee telling you that it's all just a social construct. But so I did that. I'm actually almost at the end of a economics and history degree as well, which is I guess I read a lot of history and I did a bit of economics, so I just like doing that sort of stuff, I suppose.
It's this problem of climate change is often described as humanity's greatest problem. That always seems to me to be a little bit of a vanity in that every generation thinks that's the end of the world. Is it really our biggest problem?
It's up there. I mean, it depends how close the asteroid is. There are something I'm really interested in is there's couple of dozen types of existential risks that include asteroids, that include, I've got a list here on my wall actually, nuclear war, bio war, bioterror, sort of things the sort of things you enjoy looking at when you come to work.
Exactly. I've got a list of jokes on my wall, but just by comparison.
And there are a whole bunch of things that we have that are potentially the end of the world. And climate change, I think, it's high probability that in some parts of the world it'll lead to social collapse or real problems. I don't personally. I don't think it's a proximate threat like of that magnitude to New Zealand, and I know that there are people in New Zealand who do. But I actually think the political logic, if you think that's happening, if you think that we are on the verge of social collapse, the political logic becomes pretty hideous. But it's really clear that it's a problem we need to work our way through. But the incentives, the real problem is the incentives are really poor. And we have to change those incentives, and that technology will play a big role. Habits and norms and behavior changes and trust internationally need to play a role as well. But it's not an easy problem, and I think one of the things that people who've been in this field for a long time tend to converge on is that it's going to take ages to fix it. It's not something that it's not a silver bullet problem, and there was in the case of the ozone hole as more or less a silver bullet because it was a one sector problem. It was a handful of gases or a small number of gases. It was one sector that was causing the problem, and if you deal with that sector, you're away. Well, the problem is the ubiquitous use of fossil fuels across a whole range of technologies, across a whole range of sectors, and globally. And so it's going to take a lot of work, and its characteristics as a public good are really interesting but really challenging. And I guess I feel that this one we probably can manage, and I think we can stop warming before that point at which everything would go hideously wrong. But there may be another public goods problem 200 years down the road that we don't get on top of in time. And I think the philosophy, has a pretty clear connection with those sorts of, and the policy side have a pretty clear connection with those sorts of concerns. But I'm not a doomist. I'm not somebody who I have two kids. I think that they are very lucky to grow up in a society like New Zealand, and I think they should be optimistic, but clear-eyed about the challenges ahead.
I think the tendency to catastrophize is one of the consequences of the it's an effect of the constant discussion about climate change, and it's something I've noticed in myself that I've gone from curiosity into quite a dark space and have to constantly bring myself back to remind myself that it's a problem that has a solution. And this must be something that everyone that works in this field must struggle with, and I'm sure you have as well.
Yeah, absolutely. And I don't think there's a right way to view it. Everyone has the right to conceive of the problem and the solutions in their own way, and to choose their own priorities. And one of the things that I find a bit triggering is when you get people saying, "Climate scientists, you need to do this," and I just find it thoroughly uncompelling, because it basically tries to make everybody else subservient to your specific political and social and technological agenda. And the catastrophizing, I don't think it leads where people who are new to the problem think it does. You get a lot of the same memes coming up when new people come into climate change, like the 10 years to save the world thing, where those conversations have been around for 30 years. Mm-hmm. And the fact is, every kilogram counts, and every kilogram you don't emit is a good kilogram. Every kilogram that stays in the ground is a great kilogram. And rather than saying 10 years to save the world or things like that. And the problem with the real doomism that says we're on the point of catastrophe is that if nations believe that, if they really think there's a Hobbesian war of everyone against everyone else coming, then the rational response is to rearm, not to invest in the well-being of other people through climate mitigation. And that would be a tragic, hideous world to be in. That would probably be a self-fulfilling prophecy, like the two major global wars last century.
Well, let's not go there. Let's live in a world of abundance. Yeah. I agree, and I totally am excited about the future that is an alternative to fossil fuels. It's one of the reasons I'm involved in the venture capital fund, is because the opportunities are so exciting.
The people I find most the meetings I go to where I come out most optimistic and sort of buzzing about this world are meetings of engineers and some business people, and the worst ones tend to be political scientists and lawyers. But I do think that there's changes is coming. There'll be pots of gold at the end of the rainbow for low carbon or zero carbon technologies. And when the incentives are strong enough, people follow them. And I think once it's done, then all sorts of people will pile on, and Exxon will say they were with us all along, and all those other things.
What do they say? Success has many fathers.
Yes, yeah. Well, DuPont played a blinder with with ozone hole. They quibbled about the science. And they turned up with the answer and said they agreed with everybody. And we don't have that problem anywhere near as well as we did. It's on the way to recovery.
Dave Frame, Professor Dave Frame, thanks for joining us. That was a delightful discussion, and thanks for your mahi in this area. I'm sure we will hear from you again.
Thanks for having me.
Fantastic. Thanks, Dave. That was such a great discussion. I thoroughly enjoyed it. Thanks for listening to This Climate Business. I hope you enjoyed the program. There are more episodes as well as notes and blogs on our website, thisclimatebusiness.com. I'm Vincent Heringer, and if you know someone who deserves to be interviewed on our show, email me, vincent@thisclimatebusiness.com, or find me on Twitter, vheringer. That's 2 E's, 1 R. Meanwhile, I'll be back same time next week. E noho rā.